So 9-volt battery is connected to 4 resistors for this simple circuit. What would be the current at point E? Well, E is here, so that's the whole current. So if we just find the current for the whole circuit, that'll be the answer. So this is really just 2 parallel branches. Got that red branch and this blue branch. So the red branch is 9, 7, and 2. And the blue branch is also 9, 7, and 2. So 1 over, flip it. So for my whole circuit, the resistance is 4.5. And I know the voltage, the battery, is 9 volts. So just a simple V equals IR now. So now that we know the potential at point B, with respect to point D, so here's B, there's D, the only difference between those will be whatever it drops in this resistor. So if I can find the potential drop, if I can find the voltage of this resistor, that'll be the difference between B and D. So I already found my current was 2. Here, I can just reason through this. This might be the quickest way to do it. If I've got 2 amps in the whole circuit, and this branch is 9, and this branch is 9, it's going to split evenly. So they're each going to get 1 amp of current. So the current through this resistor is 1. So the voltage drop across it is 2 volts. That's going to be the difference between B and D. Four resistors are connected in the diagram above. When the switch is closed, current flows in the circuit. If no current flows through the ammeter when it's connected as shown, what would be the value of R3? So there's no current here. So if there's no current here, that must mean there's no difference in potential. Remember, that's what makes current flow, a difference in electrical potential energy. So there is no difference here. So that means, it's coming from the battery here. That means whatever it dropped here must be the same as it dropped here. But it doesn't say that they're the same resistance. That'd be pretty simple if they're the same, R was the same, but it's not necessarily. So all I know is the voltage drop across here must be the same as the voltage drop across here. We know that parallel branches always have the same voltage. Okay, so I'm going to call the branches A and B. So I have resistors 1, 2, 3, 4, and this whole branch is A, this whole branch is B. So I'm kind of keeping them color coordinated here. So my greens are these individual resistors, my reds are going to be these branches. So the voltage in resistor 1 is equal to the voltage in resistor 2. And V equals IR. So the current, well, whatever current goes there, it's not, the whole current comes here and it splits. Some goes this way, some goes this way. So I'm going to call this the current in branch A. So the current in branch A, so V equals IR, and R, 1. So if I look over in the voltage in resistor 2, I'm calling that voltage 2. This will be the current in branch B, so I'm going to call that IB, and then the resistance 2. Alright, so let's look at the branches now. We know they also have the same voltage. They always do. So the voltage in branch A is equal to the voltage in branch B. And V equals IR, so the voltage in A is the current in A times the resistance. And these are in series, so the resistance in this branch will be resistor 1 plus resistor 3. And now the voltage in this branch, V equals IR. So it'll be the I in branch B, and the resistance in branch B is R2 plus R4. Okay, now what? Well, you can tell I'm looking for an expression for R3, and my answer can only have R's in it. Well, here's an R3 in there. If I can get rid of these I's, I'm good. Well, it's kind of a system of equations. So from here, there's lots of ways I could go about this. I could I could solve one of these for, IA and do substitution. I'm gonna divide one equation by the other. You figure if these are equal, if I divide each side of the equation by that, you can do that in algebra. Divide both sides by 3. I'm going to divide both sides by this. I'm going to divide this side by this, and this side by this. Other ways would work. It's just the way I did it. Pretty slick. So now current cancels out. Now I'm down to just R's. I just have to solve this for R3. So I'm going to cross multiply here. R2 times that I need to distribute. So R2 times R1 and R2 times R3. And then same thing this way. R1 and I need to distribute. And now if you look here, R2, R1 is the same as R1, R2, Commutative property of multiplication. Doesn't matter what order I write them in. So I'm going to subtract that from both sides. And now I just need to rearrange and solve this for R3. I'm just going to divide both sides by R2. I'm coming down here where I have room. So R3 is R1 times R4 divided by R2. And that is the same as D. I think last year we ran out of time and I didn't have time to think about this, so we skipped this one. But this year we got it. Given 4 identical resistors of resistance R, which the following circuits would have an equivalent resistance of 4/3 R. So I'm just going to go through here quick as I can and figure out equivalent resistance. So I'm just going to look at A first. Can't use the button on the calculator when my numbers are. So I'm going to figure out the equivalent resistance of this parallel section here. So that's 1 over R plus 1 over R plus 1 over R is 1 over the total. So that is 3/8. And then I flip it and I get R over 3, which is 1/3 of an R. And then that is in series with that one out in front. So there we are. That's it. That's R, R and 1/3. That's 4/3 R. Well, I'm going to try, if I had time, I'd try all of these and show that they are not 4/3 R. I'm going to do one more quick. Let's look at B. So I'm going to do, this is a parallel, 3 parallel branches. That first one has a resistance of 2R, so 1 over 2R plus 1 over R plus 1 over R. Can't use the button, so I'm going to find a common denominator, 2R. So if I multiply those fractions each by 2, I have a common denominator. So on the bottom I have 2R, on top I have 1 plus 2 plus 2, 5 over 2R, 4 over 2R. Shush! Alright, screwed up the math on this. Ignore this. So yeah, really, ignore this, but it isn't 4/3 R. A was the correct answer. Number 81. 3 light bulbs in the circuit are identical, and the battery has 0 internal resistance. Okay. When the switch S is closed, to cause bulb 1 to light, which of the other two light bulbs increase in brightness? When the switch was open, this is all it was. This is what it was. It was, just this battery, this light bulb 2 and this light bulb 3. So both get all of the current because it's a simple series circuit. But when we close the switch now we have this little parallel piece here. So for this parallel piece, remember, the total resistance of this is smaller than the smallest. So this has less resistance than just this did. So and then plus we add this one to it. So my whole circuit has less resistance, so it's going to have more current. And number 3 was getting all of the current. So here, there's going to be more current going through it than there was over here. So 3 is definitely getting brighter. But what about light bulb 2? Well, last time 2 got all of the current. Now it's splitting here. Now it's only getting half the current. Even though it's more current overall, it's only half of it goes through 2, so that is not going to get brighter. So it is C. 82. In the electric circuit shown above, the current through the 2 ohm resistor is 3 amps. I'm just going to mark that on here. What is the approximate EMF of the battery? So I want to know the voltage of the battery here. Well, I could find the total resistance. I'm going to hold off on that. I'm just going to work with this. Ohm's law for just this one resistor, V equals IR. The current is 3, the resistance is 2, so the voltage is 6. Well, I know when things are in parallel, they all the same voltage. So these each have a voltage of 6. So if I do V equals IR for this one, I know the V is 6. I know the voltage is 6. So I can finish both of these now. The resistance is 6 up here, so the current is 1. And down here in the bottom, the resistance is 3, so the current is 2. Well, remember how this works. The current splits between the branches. If 1 amp goes here, and 3 amps go here, and 2 amps go here, you can tell I have a total of 6 amps. So now, I could go back and do the whole circuit if I wanted to. I could find this total equivalent resistance, and that would work. Find that, do a V equals IR for the whole thing, find that V. That's not what I did. I thought it was quicker to figure out. I can tell the voltage drop across this one now. V equals IR. The whole current goes through there, so current is 6. Resistance is 6, so the voltage drop there is 36. And now I think it's just easier to do the Kirchhoff's loop law. If, the battery, whatever that is, minus 36, minus 6 volts here, so that has to be 42. The loop law. Number 83. Which of the following wiring diagrams could be used to experimentally determine R using Ohm's law? Well, if I'm experimenting, these have to measure stuff. Assume an ideal voltmeter and ideal ammeter. Remember, a voltmeter needs to be hooked in parallel. All the parallel branches have the same voltage. So I'm just going to glance across here. That one's not. This is in parallel with that resistor. This is in parallel with that resistor. This is in parallel with that resistor. This isn't. That's in series. That's wrong. That voltmeter won't work. Let's look at the ammeters now. Ammeters measure current. So they have to be connected in series. So no, that can't be. That's in parallel. B's okay. That's wrong. And we already said D was wrong because of the voltmeter, so the only thing that has both of them hooked up correctly is B. Number 84. If B were to burn out, so B2 here. If B2 were to burn out, opening the circuit, breaking the circuit, stopping the current flow, which voltmeters would read 0 volts? If B2 burns out, that just wipes out this whole middle section. They're just going to get rid of it. No B2 here. So now I'm just down to a simple series circuit, and yeah, it's going to drop voltage, going to drop voltage here, going to drop voltage there, going to drop voltage there. So the only thing not having a reading is V2. If B2 were to burn out opening the circuit, what would happen to the reading of V1? Let V be the original reading when all the bulbs are functioning, and let V underline, what the heck, be the reading when B2 is burnt out. Okay. So they want to know. So comparing when it was hooked up to when it was burned out. So I made up numbers. Here's my work from last year. I just made up numbers. I called them all resistance of 10. It doesn't even say that they're all the same resistance, but I made up 50. Made it up. Made up this 50. Made up those 10s. So using that, I did my whole resistance before it was burnt out. I got a current, it was 3 in the whole thing. And then if it was burnt out, it was just a simple series circuit. So then it was just a 10 plus a 10 plus a 10. Now my total resistance was 30. So then I'm looking at just the reading of V1. So just the voltage here. So it got all of the current. So here's what it was when it was whole, when the whole thing was there. Here's what it was when it was burnt out. When it was burnt out, it was somewhere between this and twice this. Does that make sense? Not loving that problem. Number 86. Closing which of the switches will produce the greatest power dissipation in R2? Okay, so here's resistor 2. Well, if you're going to get any power, you can tell you got to shut this one. So we got to close S2 for sure if we want any power in this. Same thing here. We got to close S1 if we want any current to flow in this circuit whatsoever. So S1 and S2 for sure. What about S3 though? What would that do? If you closed that, there would be no resistance in this branch. All of the current would go here. None, if very, very tiny bit would go in this one because there's a resistor here, but this would be like short-circuiting it. Remember in that FET thing when those charges started flowing like crazy? That's what would happen right here. So we do not want to close 3. Number 87. Closing which of the switches will produce the greatest reading on the ammeter? So ammeters measure current. And right here where this is placed, you can tell that's the current in the whole circuit. It's right here next to the battery. So this is asking in which case would I get the greatest current? Well, that's when I have the least resistance. So I've got to close this for any current to flow in this. I'm going to leave that open and close this one, because when I close this one, remember that short circuits, and then they start going like crazy. So closing, this time I want to close S3, and I always have to close S1.